Hello students, in this lecture I'll explain about construction and working of N-Channel Enhancement MOSFET. So if you see that Enhancement MOSFET construction is very much similar to depletion MOSFET. We need to take a P-type substrate. In that P-type substrate, two N-type channels are induced. One is connected to drain, another is connected to source. Gate is insulated from the substrate using silicon dioxide terminal. So the major difference is that initially there is no channel established between two N-type regions in enhancement MOSFET. This is the major difference between depletion MOSFET and enhancement MOSFET. In depletion MOSFET, initially there will be N-type channel established between drain and source. In enhancement MOSFET, there is no initial channel. Now let us see the working of N-channel enhancement MOSFET in two conditions. First condition, let us take VGS is equal to 0. When VGS is equal to 0, that is gate and source is short circuited. Let us see what will happen when you apply VDS or VDD in positive direction. So whenever you will apply a positive voltage to drain and negative voltage to source, the major function of this external voltage source is to induce the electrons or to make the electrons to flow from source to drain, or current has to flow from drain to source. So the electrons coming out from N channel are opposed by this P-type substrate. Since there is no initial channel created, even though you increase this VDS, there will be no flow of current from drain to source. Another thing is that the PN junction between drain and substrate will be reverse bias. You can see positive is connected to N and negative is connected to P. So this PN junction will be reverse bias and it will not allow the flow of current from drain to source. In second case, let us take VGS greater than 0. When VGS is greater than 0, G is positive with respect to source. Then these positive voltage will attract negative charges to get deposit exactly beneath the gate. So as you keep on increasing the VGS in positive direction, but one particular voltage where VGS is equal to VT, this is called threshold voltage or voltage inversion. When VGS is equal to VT, the negative charge particles which are depositing beneath the gate are sufficient enough to create a channel between drain and source. Once the channel is established, then the current can flow from drain to source and the current can be increased by increasing VDS. So second condition is VGS is made positive and VGS is sufficient enough to form a channel. Once the channel is formed, as you increase the VDS, ID also increases in ohmic region. Once it will reach its active region, it will get saturated. So enhancement MOSFET can operate only in enhancement mode. It cannot operate in depletion mode since initially there is no channel established. Only one way the channel can be established is you increase the VGS till VT. Let us take VT is equal to 3 volts. When VGS is equal to 3 volts, a channel is established. Then it can work as a enhancement MOSFET. This figure shows three different types of symbols. Most probably these two symbols are used for representing N-channel enhancement MOSFET. If you want to draw the symbol for P-channel enhancement MOSFET, simply the arrow directions need to be reversed. Figure shows drain characteristics of enhancement MOSFET. So as I said, we require minimum amount of VGS for the MOSFET to operate. Okay, so when VGS is equal to 2 volts, until VGS is equal to 2 volts or VGS is less than 2 volts, ID is equal to 0 because channel cannot be established. So the drain characteristics shown in the figure has VT is equal to 2 volts. VT is equal to 2 volts. So when VT is equal to greater than 2 volts, VT is equal to greater than VGS, VGS is greater than 2 volts, channel will be established. Then you can see the drain characteristics are similar to enhancement MOSFET. As we said, whenever you will increase the VDS, ID will start increasing in ohmic region. Once it will crosses this border between ohmic region and active region, ID will remain same. So the major difference here is what was the condition, or else whatever the condition need to satisfy for the MOSFET to go into ohmic region to active region in depletion MOSFET is VDS should be greater than VGS minus VP. But in case of depletion MOSFET, the condition is VDS should be greater than VGS minus VT. Here, instead of pinch of voltage, we are taking VT. So whenever your VDS is greater than VGS minus VT, it will operate in active region. Whenever your VDS is less than VGS minus VT, it will operate in ohmic region. So the border which between ohmic region and active region is VDS is equal to VGS minus VT instead of VGS is equal to VGS minus VT in case of JFET and depletion MOSFET. This figure shows the transfer characteristics of enhancement MOSFET. You can see whenever the VGS is negative, ID is equal to 0. When VGS is equal to 1 volt or VGS is less than VT, no channel is established. Therefore, ID is equal to 0. Whenever your VGS is greater than VT, the channel will be established and it can act like a enhancement MOSFET. As VGS is greater than VT, the ID increases proportionally. Therefore, we can say ID is equal to K into VGS minus VT whole square. When VGS is less than VT, no channel is established. ID is equal to 0. When VGS is greater than VT, if we keep on increasing the VDS in positive direction, ID starts increasing proportionality to the square of VGS minus VT whole square.